In this lesson, we will put together the concepts that we've looked at in the last two lessons and now start to look at what a UV VIS spectrum actually looks like and the features of the molecules that cause the spectrum to have certain structures. Okay, so a spectrum is a plot of absorbance in absorbance units versus wavelength in nanometers. So here we can see the UV VIS spectrum of, for example, 2,5-dimethyl 2,4-hexadiene. Okay, so it's a conjugated diene. And what is important, first of all, is that, well, there's one peak in this spectrum, and that peaks in the UV VIS spectrum are typically quite broad. Okay, so they're normally about 50 nanometers wide, so you can see that the peak here starts around 210 and ends at 260. The wavelength of maximum absorbance is what we call the lambda max, which is indicated here, and the absorbance values are typically numbers between 0.1 and 1. So if you look at your y-axis, you'll see that at the lambda max, at the wavelength of maximum absorbance, the absorbance is about 0.8. Now, what you need to be aware of is that the absorbance scale is a logarithmic scale. So what that means is that an absorbance of 1.0 actually means that 90% of the light is being absorbed. And in general, if you're doing an experiment involving spectroscopy, you don't generally want the absorbances to be greater than 1 because that will introduce errors into your experiment. What is potentially most useful about UV VIS spectra is that these spectra are actually useful for quantitative analysis. So there's a law called Beer's law, which states that the absorbance is equal to epsilon times C times L. So epsilon is called the molar absorptivity, which is also sometimes called the extinction coefficient. Okay, that is an intrinsic property of a particular compound. Some compounds will absorb more light than others will. But C is the concentration of the compound in solution. So there's a linear relationship between absorbance and concentration. And this actually becomes very useful in biochemistry because absorbance, measuring the absorbance of a solution at 280 nanometers is one way that biochemists determine protein concentration in solution, and determining the absorbance at 260 nanometers is useful for determining the concentration of DNA. And when we get to the unit on aromaticity, we'll talk about why certain amino acids absorb at 280 and why the nitrogenous bases in DNA are going to absorb at 260. And then L is simply the path length of the light beam through the sample, which is almost always 1 centimeter. You do these measurements in a little plastic or glass vessel called a cuvette that's 1 centimeter in length. So that's quantitative analysis where we look at how big the absorbance is, but you also get important information about the structure of a molecule depending on exactly where the lambda max is. And it turns out that there is a relationship between the extent of conjugation and the lambda max. So each additional conjugated double bond shifts the lambda max to a longer wavelength. Remember, longer wavelength corresponds to lower energy by 30 to 50 nanometers. Okay, so if you look at the data in this table here, 1,3-butadiene, as we've already discussed, absorbs light with a maximum at 217 nanometers. If you put 3 double bonds in conjugation, so 1,3,5-hexatriene, that's going to have a lambda max of 258 nanometers. Okay, so that's 40 nanometers longer in wavelength. And then if we put 4 double bonds into conjugation, 1,3,5,7-octatetraene, that's going to shift the lambda max down to 290 nanometers. Okay, so that's again giving us, well, now about 30 nanometers longer in wavelength from the triene. Okay, so why is this the case? Well, what we need to do is look at the molecular orbital diagrams. So refer back to the last video if you have not watched that. We have to consider the molecular orbital diagrams for all of these substances. So as I discussed in the previous video, the transition that is important that causes the molecule to absorb in the ultraviolet or the visible is always between the HOMO, or highest occupied molecular orbital, and the LUMO, or lowest unoccupied molecular orbital. And this figure gives you a good sense of what the relative energies of the HOMO and the LUMO are. So if you look at these energy diagrams, the energy of psi1 of the lowest energy bonding molecular orbital and the energy of the highest energy anti-bonding molecular orbital, whether it's psi4, psi6, or psi8, those are about the same in the three structures. But when you have more total molecular orbitals present, okay, so in the diene you have 4 molecular orbitals, in the triene you have 6, and in the tetraene you have 8. When you have more molecular orbitals present, the gap between the HOMO and the LUMO shrinks. And that shrinkage of the gap, of course, results in absorbance at longer wavelengths. So a couple of other points to make about this. If we think back to ethylene, which is what I used as the first example of molecular orbital theory treatment, there are only 2 molecular orbitals in ethylene, the bonding and the anti-bonding, psi1 and psi2 if you prefer. So therefore, the HOMO-LUMO gap in ethylene is even larger than for 1,3-butadiene, so the lambda max is outside of the UV region. It's at 190 nanometers. If you wanted to excite an electron from the HOMO to the LUMO in ethylene, you would actually need to use X-rays rather than ultraviolet light. And then another important example of a molecule that's going to absorb in the ultraviolet is benzene. And its lambda max is 254 nanometers. Now, the molecular orbital treatment of benzene is actually a little more complex than for a simple 1,3-diene or 1,3,5 triene. And we will get to that when we talk about aromaticity. But just looking at the trends here, if you have 3 conjugated double bonds, you would expect a lambda max of about 254 nanometers. And that is precisely what we get for benzene. So that's the reason why aromatic molecules are also going to absorb in the ultraviolet region of the spectrum. One example that you have already seen in lab is when you did the TLC lab, you actually shine the UV light onto the spots in order to see them. The reason that you could see those spots is that all of the molecules that you were looking at had aromatic rings in them, and therefore they absorbed ultraviolet light, and you were able to see them by shining the ultraviolet light on them on the TLC plate. Okay, so in the next video, we will take this principle and extend it a little further and talk about why some organic molecules, small percentage of organic molecules, are actually colored.